Hello, my name is Colin Adams and I'm a professor at Williams College in Williamstown, Massachusetts. And I'm going to be telling you today about tiling theory. Now, tiling theory is an area of mathematics that's fascinating in the sense that it involves very interesting mathematics and it has beautiful pictures. So what more could you ask for? Now, the theory of tilings goes back a long ways. You have to think back to early days when people were creating houses, buildings out of stones, and they used stones for the walls and the floor, and those stones would create various patterns, and people started to think, gee, I could make these more interesting, prettier patterns. And so then they started to create tilings. And so here you see a tiling which is from Marrakesh. It turns out that Islamic traditions, they have beautiful tilings that come out of Islamic traditions. Here you see a tiling. This is from the floor of a museum, the Archaeological Museum in Seville, Spain. And you'll notice that it has three different types of tiles: hexagons, squares, and equilateral triangles. This tiling is actually from a restaurant that I was in Southern California, and I really like this tiling because it has these curvilinear edges, so I think that's a very pretty tiling that you see right there. Of course, pavement has lots of different tilings. So this first pavement tiling is from rectangles. This is what I would call a non-edge-to-edge tiling, because you'll notice that some of the tiles have, they end without having the edges match perfectly. This next tiling is also a pavement tiling by a non-convex octagon. And then here's another pavement tiling with three different kinds of tiles that make up that particular tiling. So if you start looking down, you'll see lots of interesting tilings among pavements. Here are a couple of wallpaper tilings. So you get lots of interesting designs from wallpaper. This is a beautiful building, the Ravensbourne University on the Greenwich Peninsula in London, England. And you'll see that it has a beautiful tiling on the outside of the building. Very interesting tiling. Now, of course, we have three of the most famous tilings are the regular tilings by equilateral triangles, squares, and regular hexagons. And it turns out that these are the only ways that we can tile with a single shape for our tile that is a regular polygon. And so that would be something that you can try for yourself to think about. Why are these the only ones? Why can't I use a regular pentagon? Why can't I use a regular septagon? And you can actually prove it for yourself relatively easily if you just think about the angles that are going to occur on those other regular polygons. Here is a tiling with three different shapes of tiles. Again, an equilateral triangle, a square, and a star. This is a very pretty tiling. But let's ask the question, how strange can tilings be? And I want to get across the idea that they can be quite strange. So in this next example, which is one that I made, here's a tile, and you might look at that and say, that can't be a tile. There's no way that that could tile the plane. But in fact, it was constructed using a method that I will describe to you in the next module, constructed so that it would, in fact, generate a tiling. And so here's a tiling that is generated by that particular tile. Here's another strange looking tile. This one I think of as a dripping paint tile. And if you tile with this particular tile, you get this picture that looks like a whole bunch of dripping paint splotches. Here's another unusual tile. This one is, I call this the hexagonal spider. And if you take this hexagonal spider, you can actually tile with that hexagonal spider in a pattern that looks like this. Here is my favorite tile of all. It's the Voderberg tile due to Heinz Voderberg. And Voderberg came up with this in 1936. It looks like a sickle, as you see there. But it has several fascinating properties. So the first one is, if you think about trying to surround a tile with copies of itself, that sounds like that would be kind of hard to do. But this particular tile can be surrounded with two copies of itself. So here you see our tile in red and the two pink tiles around it completely surround it. Although, and this will be important later, the inner tile does touch the boundary of the region defined by the three tiles together. But otherwise it's completely surrounded. Now, of course, that's interesting in itself. But not only can you surround one copy of the tile, you can also surround two copies of the tile. So that's sort of surprising that you can do both of those things, again, with just these two tiles on the outside. Now, of course, we haven't answered the question of whether or not this tile can actually tile the plane, and in fact it can. So here's a periodic tiling by this particular tile of the plane. But there are also other tilings. This one is fascinating. This one is a spiral tiling, again, from the Voderberg tile. So that's a fascinating tile. So now let's go to the question of how do we actually define a tiling? What do I mean by a tiling? So what we want is what I'm going to call a finite set of prototiles so that all tiles are congruent to that set. And I don't want any of the following. I don't want any of my tiles to be disconnected. I don't want any of my tiles to have holes in them. I don't want any of my tiles to have cut points, as in C there, where I could remove a point and that would disconnect my tile. I don't want my tiles to have whiskers. I don't want my tiles to be connected by whiskers. And I don't want my tiles to be infinite. So in particular, what I really want is that all of my tiles must be deformable to a disk. So you see that tile on the left, I could deform it to a disk without cutting or pasting. If it were made of rubber, I could deform it to look like a disk. And that weird tile that I showed you before, even though that's not so obvious, could also be deformed into a disk. So that's my number one property that must be true for a tiling. The second property, I certainly want to make sure my tiles cover the entire plane, and that's called a covering. And then I also don't want any of my tiles to intersect in their interiors, so I want my tiles to be what's called a packing. So definition will say a protoset is a finite collection of closed sets in the plane, each called a prototile, and each deformable, another word for that is topologically equivalent, to a disk. And in this example, I have two prototiles. And then we say a tiling T with protoset P is an infinite collection of copies of the prototiles that together form a packing and a covering of the entire Euclidean plane. So in this example, you see this tiling by my two prototiles that is both a packing and a covering of the plane. If I have a tiling with just one prototile, that's called a monohedral tiling. So the regular tilings that we saw before, each of which had either an equilateral triangle or a square or a hexagon, those are all regular tilings. The same with that hexagonal spider. That's another example of a monohedral tiling. On the other hand, the tiling that we saw with the triangle, square, and the star is not a monohedral tiling. That one I would call it a trihedral tiling because it has three prototiles. We need another two definitions. We're going to say definition, any point where three or more tiles intersect is a vertex. We will consider that a vertex. And then the connected arcs on the boundary of a tile that are separated by vertices are called the edges. So this tile here you see has 4 vertices and 4 edges, and if you think about it for a little while, it's always the case that the number of vertices on the boundary of a tile equal the number of edges on the boundary of the tile. Now we have to be a little careful with this because if we have polygonal tiles, those polygons can have corners that are not vertices. So in this example that you see right here, notice that red dot. That is a corner of the purple tile and a corner of the blue tile that meet there, but it is not a vertex because it does not have 3 tiles meeting at that particular point. Okay, so in our next module, we'll talk about how one might draw interesting tilings, and then we will look at some of the possible symmetries of tilings.